My name is Josuttis, and we have to talk. Well, I have to talk, but I also would like to see some feedback. This is a talk I'm desperate to talk about, because we have to talk about a key component of what was introduced in C++20, the filter view of views in general. And you should know a few things about that, which might not be obvious. So to introduce myself, Nicolai Josuttis, I've written some books, I've given some talks, and I do C++ and standardization of C++ for more than 25 years now. So partially it's all my fault. Also, the filter view is my fault. I didn't know what I voted in. When I voted it in, I would not have voted it in that way. So let's see why I'm not that happy and how to deal with that. Because we have it now in the standard and we have to deal with it. So we are talking about a component that was introduced in C++20. In C++23, we already have some fixes for that. Couple of things I will tell you are specific to filter views. Couple of things are, in general, an issue of views. So let's see where we are. First of all, let me introduce views a little bit, just in case you haven't seen them or haven't used them a lot. So this is a little example of a function that prints a vector. The printing is done by a helper function. The helper function you see on the top takes a template parameter, iterates over the elements. So it's a generic function printing out all the elements. And as an output, you see the values of the elements written to cout. Okay. That can be done with other containers like a set. Set is automatically sorting the elements. So initialized with the same value, so you get a different output. In C++20, we introduced a few new things. So one is you no longer need template parameters to have a generic parameter. Instead of saying for some type called or named call T, just use auto. But this is still a template, a function template. It's just that you have a different syntax for that. And you can qualify this by saying we have concepts, to some extent require or constrain this function template so that the passed argument has to fulfill a couple of requirements which are specified under the name. It has to be an input view, input range. Roughly speaking, that means we can iterate from begin to end with using this object. And that's roughly it. Yeah, begin has to be in front of end and so on. Okay. So now let's come to views. Views were introduced in the way to say, well, yes, we want to have some collection, some range, and we want to only deal with part of it, or we want to deal with the values of it in a different way. But we don't want to create new temporary objects, new temporary containers. And so you can define a view. The basic way to define a view is to say, well, let's take a view, let's call a function, a factory, no, excuse me, an adapter that gets where do we iterate over and say something what we want to do with this range. So in this case here, we say, let's only take the first three elements. You can pass that to print. So obviously, that is still something you can iterate over. So we print the first three elements here. Now, the interesting part of this is we have a different syntax for that, another syntax, which allows you to use the pipe symbol. Well, which is the bitwise OR operator, what we use it as a pipe symbol here. So a collection can be piped, whatever the type is, into a take view, and the take view then says, oh, let's use 3 elements of that. This looks like Unix pipes, but it's significantly different from that. We will come to that in a moment. So we pipe this into a take view, and we can further pipe this into a transform view, taking the value and saying, let's convert it to a string and append an S. And as you see, the print function will now print the first 3 elements of this collection as a string with an S behind. Good. So there are a couple of other examples, pretty compelling examples, how nice this is. So you didn't see a filter view yet, so let's start with it. So let's have a map of composers of classic music. Let's iterate over them, but with some views. Let's filter out and only use those who were born after 700. Let's take the first 3 of them, and what we have here in the map is key value pairs. Let's only take the keys, which means we only want to have the names. And that's what we iterate over. And when we print out these elements, these are the strings, the corresponding strings, and you see the names here printed out. Here's a third example. Views not only are views that adapt existing ranges, they can also themselves generate values. The key aspect is that they are not heavyweight. So it's not allowed that they store a lot of elements, well, with some exception. And so they usually should be easy and cheap to copy. That's the point we would like to have. So IOTA is also a view, but not in the middle of a pipe. It just, at the beginning of a pipe, you can say, let's generate all the values starting with 1. This, by the way, is a view that is unlimited. It will generate forever. If you loop over it and don't stop the loop sometime, this will loop forever. That's, but let's only take those values that are multiples of 3. So here we see a filter. Again, let's drop the first 3 of them. Let's take the next 8 of them. So here we have a limit that we don't have an endless loop here. And let's transform to a string appending an S. And voila, that's it. You see the view is defined before. We put it on the right-hand side of a range-based for loop, and it works. Awesome. So that's the point when I give trainings about C++, everybody says, great. I want to have that. Well, there's nothing in C++ great. Well, without a but. So that means be careful. There are some issues. There are some things you should know to use things right. And we will concentrate on the filter view to look how to use these things right and why you have to be careful here and there. So to talk about and explain that, I don't want to show you symptoms. I want to explain how this works so that you understand yourself the symptoms and can see them coming. So that means let's look how views work internally. So think about, we have the following situation. We have a vector, and then we want to print the elements. So more or less, every function that prints the elements of some range, some container, some sequence of elements, iterates over the values from begin to end. So it doesn't matter whether you call it directly, you might call this indirectly using a range-based for loop or whatsoever. But that is the essence of our code. That is what always has to be called to iterate from begin to end. So let's take an iterator, initially referring to the first element, then why we're not at the end incrementing over the loop, and for each and every value, we print it out with a star, and we do this except with the last element, because that's the end. That's the position behind the last element. Remember that. That will be important in a moment. Good. So essentially, when I let in my assembler called print run, it calls begin. It gets back the position of the 47. It goes to the value, prints it out. We increments to the next value, prints it out. Next value, prints it out. And this is done in a loop by always calling AND. So if we write that loop that way, you can write it differently. We call begin once and AND multiple times. That will be important. Good. Now, that was how to iterate over a container. Now, what happens if you have views? Well, views are not working like in Unix, that you say, I start to process all the elements and store the resulting elements in a temporary buffer so that the next element of the pipe can then process them using a couple of parallel running processes. This is a totally different model. This is what we call a pull model. And the pull model works the following way. We don't compute anything, any element and any value, unless somebody asks to do so. So what you specify for that, when you specify, let's pipe call into a filter and let's pipe that into transform, is you only declare a wrapper around the collection and then a wrapper around this wrapper. So essentially, these two lines you see here are equivalent to what we pass to print here. And you see that the wrapper of the filter just refers to the original range, the underlying range, and just saying, I only let values through that are less than 20. And then here, the transformation view says, I refer to the other view, and whenever somebody wants to have a value, I have to negate it. All of these levels, all of these layers provide the same API. With begin, you see the position of the first element. With star, you see the value. With AND, you see the position behind the last element. With plus plus, when you use the iterator that was returned from begin, you get to go to the next element, and you can, with equal, equal, or not equal, check whether you are at the end or not. Containers provide that APIs. Filters do that. Transformations do that. All views do that. So now, how is that implemented? So what happens if we start to run this loop? Well, the first thing we call is, we call begin to get the first element. So this call goes to the transformation view. That delegates this to the filter view. That delegates us to the collection. So we call a sequence of begin calls. We come at the beginning of the collection, and the collection says, yeah, here's the first element. It's what I give you back the position of 42. So it's not 42 what we get, it's an iterator to 42. So the position of 42 or reference or whatsoever. So filter gets it. Filter has a task to give back the first element here that is less than 20. Well, to decide whether it's okay to let it through this element, the position of this element, it has to look at the value. So, and the value, that means the filter will call star for that. Look at the value and then say, oh, no, that's not less than 20. That's not acceptable. So what does the filter do? The filter still in the begin call. The filter says, oh, let's increment to the next value. So it goes to the container and says, please give me the next value. And that comes now Well, again, what the container gives you is the position of the next element, and then the filter called star to look at the value. So already in this phase, filter has called begin star plus plus star to find out whether this is the right first position of an element, not the value. Because the filter returns an iterator, not the value. So the filter says, oh, okay, that's okay. So let's hand out the position of the 11 to the transformation. The transformation will then say, wait a minute, I don't need to look at the value yet because we only have to give back the position. I just pass the position back to position, and that's the end of this call. Position now is initialized. There were a couple of hands up. Why?
Does it not also have to call end?
It also has to call end. Yes, you're right, because when I call plus plus, of course, I have to find out whether I reach the end. Yes, you're right. So even this initial begin will also call end. You're right. Same question there? Awesome. Good. So, done with the first call. Well, we don't have the value. We have the position of the first element. And now let's call star. Well, star, we go along the chain and go to the container. Container says, oh, here's the 11. That's the value. Value is passed through by the filter to the transformation. Transformation says, wait a minute, for each and every value, I have to negate the value. So it gives back the negated value then to the calling side, and that is printed out. And that way, we iterate over the container. So next time, from the outside, we call plus plus. We try to find the next element with the help of the filter. If an element doesn't fit, the filter will automatically not only call once plus plus, it will call multiple times plus plus, comparing with end, just that I don't forget that. And yeah, and then whenever we need the value, we will call star. Star will just be transparently passed through the filter, but here the transformation will do something with the value. That's how it works, yeah. Oh, why is the star called twice? Well, because in general, we should not cache all these values. We could, but the filter is in fact really not caching the value because it might not, you might not call star again, you might call come back, etc. And caching it needs space. So it's really that filter looking at the value called star, and also at the end, when we call then star, we also look at the value. And so, yeah, twice we look at the value in this situation.
I mean, when V2 is looking at the value, it does the star, does it have to be checked again by V1 filter and then be passed to V2, or is it a direct access?
It's kind of a direct access. So, yeah. So, this is a simplification of what I specified. Some useful things are done here. Some of the functions are just inline functions, so are optimized away. So roughly, it works well. But it's good to know that, well, the filter very rarely caches values. That is, for example, one thing here. Yeah. Say it again. What happens if we change in between? That's a talk about. So then things become interesting. So, yes. Good. So first of all, let's see that we got everything right and understood. That's a basic principle we have. We call this a pull model. So next element, so next iterator, next position of an element, and next value is always computed on demand. What is the performance of this? Well, first of all, you might be very worrying that we have so many functions involved and they play together, etc. So again, collection pipe into a filter, pipe into a transformation. That is what we just see here. Well, let's add a print statement, and just to prove that I was right, I told you right, yes. Filter looks at the 8, rejects it. Filter looks at the 15. The 15 is passed to transform, and that is then passed to the range-based for loop, which is internally iterating and asking for the first element and then for the value. And then we have the right value, which is minus 15, and it's printed. Well, in this case, the filter keeps the value, but there is another version of this, which is transform and filter are called. So when transform and filter are called, then the following happens. The transformation has to be done before we call the filter. So when we start the loop, we will have this output. So the transformation, well, we ask for begin. Begin goes to filter, filter goes to transform, transform goes to the container. Container gives the position of the first value. Transform says, oh, wait a minute, I need the value there. So it called star. And so that, well, but transform only needs the value when you ask for it. So the question is, when are you asked for the value? Well, transform just says this is the first element and passes it to the filter. But the filter says, oh, I need the value to decide whether I let it through. So that means the filter goes back to transform, via transform to the container and called star to say I want to look at the value. And that value is then sent back. So that's why we get a transformation here. And the filter got the minus 8. So here, this value requires that we have called star already, and then rejects it. So then we get the next element, and that is transform gives us the position of the 15. Filter asks for the value, gets the 15 as a value that the filter lets through. Well, but transform had to transfer it into minus 15. So, and then this filter is passes this position of the 15 to the end loop. The end loop gets only the iterator. And then in the end loop, we ask once again for the value because we want to print out the value. So that means once again, we go this queue and say this chain and say we want to have the value. And transformation once again has to compute the transformation to the value 15. So therefore you see it twice here. The filter needed once and to decide filtering, and then the caller finally needs the value. That's the next time we look at the value. And really transform is called twice here. That's not good. Well, maybe. Is it bad? Is it good? Is it not so good? But this is a problem we have. The first problem we have is a filter. A filter might lead in this chain to the effect that at least for positive values we let pass through, and where at the end a user wants to see the value, we have to look at the value twice, once to decide yes or no, and the other when the user wants to see the value. And that, by the way, happens with each and every filter once more. So that's a good thing to say, well, use filters early. Or avoid expensive stuff before using them. Is that already a showstopper for the whole game? No, wait a minute. Compilers optimize a lot. So here we have a range pipe and a filter to transform on the right-hand side of a range-based for loop. Come to that in a moment. And that is what is essentially compiled. Everything else is inline code. All the views are just 1, 2, 3-liners, inline functions. Everything is optimized away. So what you essentially program is kind of this. You say, let's iterate from begin to end with an iterator. And to decide whether we want to process the element, we have to look at the value once to decide whether it's a multiple of 3. And then when we let it through, we have to look at it again to pass it to somewhere. And if we have, in addition, a transformation before the filtering, that means before we look at the value, we have to do the transformation. And when we look at the value again to process it, we have a transformation. So the question is this bad code? If this is bad code, then you have a problem with this code. Compilers optimize when they see, well, two things happen very often the same way. So minus star pos is called here and there. So that might be optimized. The other thing is minus might not be very expensive. But of course, if minus is computing and finding out whether this is a prime number or doing some very long-term stuff, of course, that's a problem. And if that's the case, you might better do some different things, like first of all, taking the result of the transformation into a temporary container and then use the filter. That was a question. Okay, good. So that's the first thing about performance. This is pretty new. Still, compilers can improve the way they optimize code for views because every typical code has some special flavors. So it could become better. But in principle, we run into these problems or into these issues. But there's more. We have to talk about each and every individual operation. We have to talk about begin, and so on. So let's look at a vector, and let's look what it means if we filter the elements in this vector to say, let's take only the elements that are greater than 9. If we call begin, then what this does, and you saw that, we call begin in the vector, and then we try to find the first element that is greater than 9. So we have to call star for the value. If it doesn't fit, call plus plus, and you're right, and I'll call end to compare it. Right, I learned it now. And yeah, and you have to do that in a loop until you have found your first element that fit. And that, by the way, doesn't matter where the filter is operating on. So if you have a linked list, you more or less do the same. It's just that plus plus is takes a little bit longer. So begin means let's iterate over the elements until we can find and return the begin of this container. So begin for a filter on a vector, begin for a filter on a list can be pretty expensive. That's not good because in general, we assume that begin is a cheap call. And that is what we are used from containers at least. So how do we deal with that? Well, the goal is that we do not provide too expensive operations. Well, that's a general goal. That's why you cannot call the index operator in a list. You cannot call push front in a vector because these would be expensive operations. At least we want to protect you a little bit from doing that accidentally or without thinking about it. So the same idea comes here in when we deal with the design of views and here of the filter view. So the question is, how expensive is begin? So think about we want to have the multiples of 4. Well, we can see what this means. Begin might be as expensive in a way that we have to iterate through some elements. Now, the interesting question is this: what happens if we double the size of this range? Does it get worse or not? That highly depends on your use case. So if you have a couple of values, just 1, 2, 3, and all the time they are distributed over your collection, just doubling the size does not mean it's getting less it's getting worse to find the begin, because at least if values are pretty equally distributed. Well, if 4 is only once, runtime there, and you search for the 4, you filter only the element that has a value of 4, it could happen that begin has to go over all the elements until the end. And that means conceptually you can say, or you have to say that begin has linear complexity. So the more elements you have in the container, the more time it might take to call begin. So we are slow. We have to compute the predicate for all leading elements, for all elements that do not fit with that. So call begin and forward until you reach the first true. That's roughly what we implement here. How about AND? Well, AND is interesting. We wanted to have it cheap. So you might think, now AND is a position behind the 12, but we can do it even cheaper. We can say, well, no, AND is the end. Awesome. So that's a cheap operation because we just pass AND through the filter. Good. How expensive is empty? Linear? Why? Yeah, we just call begin and end and see whether they are equal. That's it. So yeah, so same as begin. How about size? Linear, but worse linear. So begin only has to find the first element, while size has to look at each and every element from beginning to end until it has an answer. So it's slow. This is bold slow. This is light slow. Okay. It's both linear, but complexity is not always good enough to see the difference between these two performance aspects of the view. Front, give me the first element, the value of the first element. Linear, yeah, that's like begin. We just call begin and look at the value. Good, like begin. Back. Oh, it depends, I would say. The question is, can we go backward through this? So if we can go backward, we go to the end and then we iterate backwards to the first element. But the bigger the element is, we have the same problem as with begin. So back is somehow slow, yeah. It's an interesting question. What does it mean if we call this and you have only a forward range? Then it gets worse. Index, jump to the 10th element. Yeah, we have to look at begin and then from that count, find the 10th element that fulfills the predicate. So we have to, the same problem as with begin, but a couple of times. Yeah. So that is the situation we have. We don't like expensive member functions, expensive operations. So let's not provide them unless it doesn't make sense, or it has to be. So what you see here is roughly what each and every view in principle could do. In fact, all the view types are derived from the base class that provides all these views, all these operations, provided it makes sense. And that is, they have constraints using the new feature of concepts. And with these constraints, size and the index operator are not provided for a filter. So the others are. So back, for example, front, empty are provided. Good. Can we improve the situation a little bit? Yeah. Oh, then the designers of the filter had a great idea. the great idea was when we call begin, and you might indirectly call begin by calling empty or front. Once we find it, let's cache it into the view. Awesome. HubSutter today said, yeah, caching helps. Okay, we'll see what the consequences are. So that happens all the time. We have other views that cache. So sometimes it gets really funny because they cache on a list but not on a vector. But that's a different story. That's other views that have other problems. So they cache whenever they have, for the first time, called begin, which might be they have just called empty, because empty calls begin. Okay? Here are the C++20 views that cache. Some of them cache always, some of them sometimes. Good. So that means, look, coming back to the slide, that the slow operations we have are maybe not that slow. Well, they are slow only once. And in combination. So if somebody called empty already, begin is no longer slow. Good. That's an improvement, isn't it? Good. So the only available and really slow function is back. Okay. So this, to make it a little bit more technical, what does that mean? If you compare ordinary containers, you call begin and size and empty. It's all constant functions. It doesn't matter how much elements you have inside. But with a filter operating on some container, the first begin has linear complexity. The second and further is then constant. The same is true for empty, and size is not available. Good. We have a term for that in the C++ standard. It's called amortized constant. This is amortized constant. The call of begin has amortized constant complexity. So you might have heard that term before in vectors when pushback is called, you insert an element. So the first time you insert, you might have to double the memory. That takes a lot of time, and the time depends on the number of elements you have. But then you not just add one space for one new slot for one element, you just double the size or so, or add 50%. And that means over time, this penalty amortizes, so that over time, calling this multiple times, we have an amortized constant complexity. So that is the case here, but it's a little bit of a fake, or maybe good marketing, because in a vector, I would say it's pretty likely if we insert one element, we will add more elements. Now, the interesting question is, if we call begin once, will we call begin more than once? And my prediction is that's not that likely as for vector calling multiple times pushback. Because if we iterate, we only call once begin. So be careful. And by the way, we have a concept for ranges. And so that a view is a valid range, we switched just for views, we switched to the statement that in a range, the requirement is that both begin and end have amortized constant time. So not constant time, amortized constant. So sometimes it might be expensive. So drop is a little bit funny. Drop sometimes has this problem because it caches only when it works on a list, not on a vector. So changing the underlying container might switch from constant complexity to linear complexity, just calling begin. But that's here not the drop talk, that's a filter talk. But it could be worse than with a filter. So what are the consequences of this design? So this looks like an improvement, but we pay a price. The price is the following. guess you're starting with views. You want to play games with this cool new feature. So, let's pipe the vector into take view. Print only the first 3 elements. Awesome. Let's pipe the vector into a transformation, negating the elements. Awesome. Oh, it's great. I love this technology. So let's pipe the vector into a filter, and the predicate is let's only accept the elements that are greater than 9. I want to see the result, but compile time error. Wait a minute. Why is that a compile time error? You should see the error message. It's a little bit strange what it says. Somewhere in between the code, there's something wrong. Let me try out something. Let me see. So that means you cannot pipe a vector into a filter. Let me directly use it in a range-based for loop. Oh, that compiles. Wait a minute. So we can iterate over the elements of a vector, the filtered elements of a vector, when it's directly on the right-hand side of a range-based for loop, but not when we pass the whole thing to a generic function iterating over the elements. So this is a moment where each and every programmer, starting with having the first early adoption of views, gets crazy. And the usual reaction in C++ is now, it's my fault, and I always learn C++ is too complex, there's something wrong, I'm an idiot, forget it. Go to Rust. What happened? Anybody guessing what happened? It's not const when it works, but here it gets const. Yes, the const is the problem. And why is const a problem? Because we cache. Because when we call begin, we cache the result. And that means we modify the view. It's that easy. How about mutable? We will answer that question in a moment. So yes, that is the effect. No warning, nothing else. It's just, you have to know that to understand the problem. So, and then you need a workaround. How do you deal with that situation? So there are a couple of ways to deal with that situation. Let's just for fun go through some of them. So you can say, let me define this filter view, and then pass this filter view to a subrange. A subrange is also a view, although you cannot create it with a helper function, so you have to use studrange's subrange instead of studview's subrange. So we are not that consistent in this library. And then what does subrange do? Subrange is a view that at construction time calls begin. So it does not have to call begin later, which means we compute it during initialization. And with that, we can now use that to iterate even later, calling begin again and again. So that's a whole trick. So I only have to teach to programmers, do that. Well, this is the beginning of the talk. Let's see, what time is it? Okay. So, by the way, for some reasons of class template argument deduction, you cannot pass the whole thing just to subrange. You need these 2 lines. Yeah, that's the question.
Realistically, is there actually ever going to be a scenario where you won't call begin in some form?
Is there a scenario where you won't call begin?
Why don't they just cache begin value on construction of the view?
Oh, why don't we cache begin value on construction? That is an interesting other optimizer. So now you are questioning the design. I just wanted to deal with the symptoms. But okay, let's talk about the design. So the reason we don't cache it in the construction is that makes construction expensive. You might never iterate over the elements. So the design decision was, it's better to delay the construction, the first call of begin, until we really know we need begin. That's a design decision. You could have done it differently. Good. Okay. There's other options. You can use a universal reference. Well, the standard calls it forwarding reference, but that's a lie. It only sometimes is used for forwarding, for perfect forwarding. Here, it's really a universal reference. It can universally refer to everything without making it const. Because we need a function that takes both R values and L values, so objects with names and objects that are temporary. And for that, we have universal references. And with that, the code works. So I only have to teach to each and every programmer and to go through all my generic functions that take a container and convert to a universal reference. Awesome. But be careful. Now, here was the question, why didn't we hide caching? Why didn't we say, let's internally make things mutable? Well, be careful. If you do that, or if you do it that way, you have a problem. The call of begin is no longer thread safe. The call of empty is no longer thread safe. Which means if directly or indirectly, two different functions use the same view at the same time and call at the same time begin, directly by iterating or indirectly by calling empty or front, you have undefined behavior. So having this ruled out, well, this would be a problem if I do it that way, for example. But it would be enough to say one thread calls empty, the other calls front. That is undefined behavior now, which is a break of what we have standardized for containers. In containers, there's an explicit statement in the standard saying begin is thread safe. It's always considered to be const, even if it's not const. So, therefore, if you do that, you better take the argument that way because that protects you from this problem. So that was the reason probably the designers of this library thought mutable is not the right answer because then you hide this even more. If you use mutable, you should then internally use mutexes. So you should make your cached begin somehow atomic or protect with a mutex. Yep.
You're now using auto-reference, and on the examples on the slide beginning, you at some point switch to the concept of a view.
Yeah.
Forward view, I guess. Would that work with the filter view as well?
Yeah, you can even in front of auto, you can also write this is a std range input range, and you can write it in front of auto and still use it to ampersand.
So the filter view there would work too, despite begin not being constant.
Yeah, because, well, at the begin we use const reference. That does not work. Yeah. So if you use to ampersand,
Okay.
then you can still qualify it with, in addition, qualify it with some constraints. There's another option. We can take things by value. So that was an interesting answer given when this was discussed. Because, yeah, one of the key designs of a view, it's cheap. It doesn't contain any elements. So it's cheap to copy. So why don't pass it by value? But the problem is, we might want to call this function with both containers and views. So passing by value would make calling print for a vector expensive. So maybe we require that the parameter is then a view. Yeah, we have concepts, and we can say, yeah, here's a constraint that this function is only available for views. But then printing a vector does no longer compile. Okay, can we somehow make it a view? Yeah, there's a way to say, let's take all the elements and make it a view. Well, put a view as wrapper around them. The view is called all. Let's take all the elements, but make it a view. And now it works. I only have to teach that to the programmers. Okay. And there's another option you might say, but wait a minute, maybe we can do it the following way. For views, we take by value. And then for containers, we take by reference. So that's overloading. So the one on top should be more special than the one on bottom. That's, by the way, not true. Because it's not that usually you can say something more constrained is more, has higher priority than the other, but unfortunately the rest of the signature is not the same. So there are different rules when which is called. So what you have to do then here is not just to say that has no constraint, you have to say, no, and this is not for views. So we require this is not a view, and then we call the below the print, and otherwise we call the upper. So the only thing you have to do is all your processing of containers now to make them viewable, you need two functions. You like that? No, me neither. Good. And somebody said that, how about when we modify elements? So far we didn't modify elements. So now comes the real fun part of the filter view design. This is a very, very simple program. Vector having 4 elements, and we call print. Now, let me define, I want to deal only with the even elements of this collection. So that would mean I define a filter operating on this collection. And the predicate is modulo 2 equals 0. And now let me use that view to modify the elements. What this means is we want to find the even elements and we do something with them. This can be a modification. All good. So we can modify the value. Adding 2, okay, now we have 1, 6, 7, 12 after that. Do it once again. We have 1, 8, 7, 14 after that. Awesome. Works. Yes, you can use views to work with ranges, even when you want to modify the elements. Let me try something different. Let me add 1. Okay, works. Awesome. So why the hell is this guy coming up with these crazy slides? This will, of course, work. Why not? So let's call it once again. Oh. Oh. Oh my God. Oh, we use that view another time? Well, yes. The first time we used the view, we cached begin. That's begin. The second element is begin. Now using it another time means we start there. And then starting there, we only cache begin, but from that we double check the values before we process them. So that has this nice effect. Okay. Well, we are not stupid in the standard committee. Well, maybe we are, but this is officially a runtime error. Well, the runtime error is precisely specified as follows. For a filter view, we have the following statement. Modifications with the filter view iterator is permitted, but results in undefined behavior if the resulting value does no longer satisfy the filter predicate. So, problem solved. You only have to know that rule, and you won't make this mistake. We heard in the keynote today what this means. Okay. And an interesting example that another guy in the standard committee came up with is, oh, so that means I cannot use a filter view to heal broken elements. I cannot use a filter view to heal broken elements. So you look, for example, in your computer game at the monsters and look for them who are dead and you want to resurrect them. That's undefined behavior because they are no longer dead. According to this statement, you have made a mistake in your program. It's not a compile time error, it's a runtime error. Well, you can burn them, provided this will not resurrect them. So you never know with monsters. Okay. So first time it works. So maybe we only use the view always the first time. So instead of defining the view and then using it twice, let's use it only once. So we only call once begin. But why then do we cache begin? If that is the solution? Okay. When I was at this point, understanding what we designed and have standardized, I really got a little bit sad. So the next guideline is use and reuse views ad hoc. And that applies to the filter view. That's better, at least if you modify elements. So, but it gets worse. So it's not only that we might modify the values, it's also that others might modify our container. Well, in principle, anything can happen if you iterate over something that is getting modified, for sure. The question is, can we somehow allow some things, maybe when we think with our hand and see this should have worked that way, so that should work, that should be safe. So look at this example. We have here a vector in the list initialized with 4 values, 1, 2, 3, 4. We call drop on that. And then we insert some new values. And then we call print. And then we call insert. And then we call print. Now, the drop view is a little bit tricky because it caches sometimes. It caches on a list, but not on a vector. Well, a filter always caches. So when we do the same with a filter, sorry, this example is not using the filter, we would have the behavior which you see here for the list in the second row. That would be the behavior if we use a filter here. I should change the slide. Finally, if you copy the cached view, the cache is removed. So suddenly it works again. But the real problem is the following. You don't understand what's going on here. So let me add a print statement. This print statement changes the behavior of the program. Because we cache earlier. Oh my goodness. We have honestly standardized a component in the C++ standard library where read iterations change or can change the state of a program. And that is the case when we cache and because of caching. We cache earlier, so before we add another value, so okay. Well, don't get me wrong. If you modify, you cannot protect yourself against everything. If you modify a value and you have a filter view and you go forward and then you go back and your predicate no longer applies, there's a problem, for sure. But here, we just iterate from begin to end. So why shouldn't it just work the way? Let's restart from beginning with this predicate and all is good. Yeah, because we know why, to make begin cheap. But as a consequence, we learned you better use it ad hoc. Okay, so we come to the interesting question, is caching worth it? So here are the roughly a matrix where using the filter view is fine or using a filter view is broken. So you have just one iteration from begin to end. If you only read, great. If you modify and keep the predicate valid, fine. If you modify and break the predicate, you have undefined behavior, but it works. The first time only the first time, one iteration. If you have multiple iterations from begin to end, similar, it's just that from the second iteration it no longer works. If you start not just to go from begin to end, you go back and forth and back and forth, obviously, if that breaks the predicate somewhere, the modification, suddenly there is something strange going on. It will not work properly anymore. And that's for sure something that's inherently in the problem. So that is nothing we can fix. That's not a surprise. Concurrent iterations, even if we read, are broken. And concurrent calls of begin, front, empty, and if is also available, so is, which is the opposite of checking whether it's empty, is also broken. You should know that when you use the filter view. So please note, the blue slots in this matrix are the ones that are caused by caching. So without caching, it would look like that. So read would always work. Oh, that would be great if just read would always work. And here we also have no issues. We would not have this strange undefined behavior where we are trying to fix elements. So the question is it worth it? All the traps, all the problems you saw, is it worth it that we cache? So let's look. What is the benefit of caching? So yeah, you saw a second call of begin is cheap, but which is the use case that helps us, where it really gives us benefits? So let's take a look at some examples. So we have here a range that is piped into a filter. And this filter just wants only to use the elements that are not zero. So this is just assuming maybe a very typical situation where you say, yeah, you have a couple of values, some of them are zero, some are not, in some distribution. Okay. The usual way we iterate is we call begin, and while we are not at the end, we call plus plus, which means we call multiple times end, we call only once begin. You can program that differently, but that's a very typical piece of code you write to iterate over elements. So the first iteration has to find begin, which here is 2 elements ahead. So we go to the third element. Pretty okay, I would say. And then we iterate, and with the iteration, we iterate step by step over the other elements. For that, while we iterate, we have to call end a couple of times, even to find the first element, to know that this is not beyond the end, so there is none. So, but end as is cheap. So green, cheap, yellow, red means, yeah, we have to linearly visit each and every element there, independent from whether these elements fit or not. And a second iteration is in that way optimized by this optimization that we say, and then when we use the same view once again to call another time begin, that is cheaper than before. How much cheaper depends on how likely it is that there's an element early that fits the predicate. very different use cases can exist there. So we have few benefits from caching, I would say, in such a use case. I would say in this case, it's not worth it, but maybe I'm wrong, and it always depends. So let's come up with another use case. Let's assume we have only 1 or 2 elements in the middle of the range that fit our predicate. So there's a significance distance from the beginning. So the first time we call begin, we have to look at each and every element, and then we iterate over the rest. By finding the begin, we also have to call end, and also while iterating to the end, we have to call end. So we call a couple of times the green function here, which is cheap, fortunately, because we don't do anything there. And in a second iteration, yeah, we have significant improvement. So we benefit from caching when we a second time iterate over the elements. Please note there's a special corner case that your first iteration of your first finding of begin might be you ask for the size. Remember, when we ask for the size, we already call begin for the first time. So calling size and iterating all the elements is here already better. And of course, the later the first match comes, the better is the caching. In the example you saw here, we had and and was right behind the last match. That's here. Well, what happens if we don't have that something? Well, I told you that already, which is we do not cache and. Well, we know what and is. We make it cheap. We don't cache and in a way that we say and is the position behind the last element according to the predicate. So even in this scenario, and is there. That is not good because that means, yeah, we benefit from optimizing begin in a second call. We benefit from that. But in the second iteration, we will still iterate over all the elements from the middle to the end, although this is not necessary. Yeah, in this case, we clearly could say, well, let's only iterate twice, and here is the end, and that's it. This is not implemented in the filter view. It is not. Is that a good decision or not? Not sure. So we benefit from caching in the second iteration, but not from caching for the remaining elements. So if there are a lot of elements not fitting your predicate, that's not a good situation. Or you just have your element right at the beginning and nowhere else your match. That will have bad performance, unnecessarily bad performance. And it's always about at least once we have to look at each and every element because we have and compare against and we have to look at all the elements. Well, at least when we iterate after we found begin. Good. So is there a use case where just the first iteration pays off? Yes, there is one. Well, there are a couple, but the interesting thing is what happens after a filter when we have a pipeline? So maybe the thing after a filter, for some reason, causes multiple calls of begin. So the example is reverse. Because reverse works the following way. If somebody calls begin from the outside, we map it to end, and the other way around. Well, we have also deal with one offset, but that's details. So that means if we have that situation, and we call begin. So for the thing as a whole, this is by reverse mapped to a call to end, which is where we are. And then from there, we try to find begin, and we iterate, and then we call begin, and we compare with end. So each time we compare with end, we call begin, and begin is now computed. And begin is, in this scenario, called multiple times. So first begin is expensive, but then after that, each and every other begin is cheap. So this already might happen on initialization. And then when we start to iterate to find the other elements, we call begin again. So the first begin might be called multiple times because we iterate to find begin. And while we are finding begin, we have to double check that we are not at the end. And the next thing is when we are there, here's the real iteration. Here should be a green arrow. I don't know where it has gone, but okay, it's there. The next time we have a second iteration, we also benefit from that a little bit more even because the first begin was also already cached. So that means no more expensive begin calls here. So there we have, and that's the point, even in the first iteration, a benefit from caching. Well, unfortunately, or fortunately, this is not the way usually, well, at least in the standard library, we work. We are not that stupid that we call begin all the time, again and again and again and again. So the most important example is the range-based for loop. The range-based for loop is not working that way. The range-based for loop is essentially working that way. It says, let me call once begin and one end at the beginning, and then we iterate just comparing these two values I've computed only once. So which means, yeah, we only call begin and end once, and that means we call this begin only once, and that might need that we need or once to get it here and once then to start the loop or end the loop. So yeah, so multiple calls of begin are no longer there. That's one inside the view and then what's one outside. We still benefit from the second iteration, but the benefit here is not the best. And again, we have the scenario where we will iterate over all these values because end is not cached. Do you like the design? Well, so not consistent is an interesting answer, yeah. Good. So, you can do better, by the way. So I have some programs that measure all these scenarios, and you can really measure that where the time is wasted. And so I just for fun did the following. I said, oh, maybe I cache myself because I can do better than the filter. And because what I can do better is when I know it's worth it, I can say, let me compute the begin and let me compute the end, but the real end. So the one slot behind the 5. So let's do that. How do you do that? Yeah, you can write your own helper function to do that. But can you also compute begin and end with views? Yeah? Filter off from the reverse to cache end. But we also need to cache from begin. So we want to have both. Well, yeah, you can say the filter does the other anyway. But just for fun, I had the task, maybe I want to myself write a perfect cacher for this. saying, let's compute the beginning and end of this. So how with view tools could you do that? Subrange? But the subrange is just, well, the subrange does not compute anything. You can initialize the subrange with some begin and end, but how do you compute begin and end? Well, here's a trick. Take the range and drop while there are zeros, then reverse and drop while there are zeros, and then reverse again to have the right order again. That's a magic trick. And then you can pass that to the filter, because there might be elements inside that match or might not match. You cannot just take all of them. Yeah, and if I do that, and I measure that, and I look into my code base and see now, how fast is that? Oh yeah, awesome, that's really fast now. Now, just iterating over the elements is really incredible fast. Doesn't matter whether I go forward or reverse. Okay. So is caching worth it? The caching we have implemented in the filter? I don't know. That's maybe a different question. A final note though, there's another issue with views. It's regarding constness, and that also affects the filter. If you wonder what is the exact type of a view, it depends how it is created. And one of the key questions is, does it run over a range that is an R value or over a range that is an L value? So when we initialize a filter on an L value, so on a container or on a range that's there, we can easily say, oh, you know what, this is just referring the underlying container. We cannot do that if that is a temporary object, because the temporary object will die at the end of this statement. So in that case, we do something different. We use a so-called owning view helper. So both filter view just delegates the question how to deal with the data it gets when it's coming not as a view but as a range, in the following way that it either uses a ref view or an owning view. The ref view refers to the existing object. When it's an L value, we can go with that. When it's an R value, we move the whole value into the view. That is the example where even a view can have multiple elements stored. But to some extent, that's not expensive because they were created before. We just move them into the view. And yeah, that's a general issue we have. By the way, owning views were not part of the C++ standard. Initially, this would not compile. They came as a faked bug fixes. So it was not a bug fix, this was a feature increasement, but we called this a bug fix. And so it's part officially of C++20, but you will not find anything about owning view in the C++ standard manual, C++20 standard manual. We will find something in the C++23 standard manual, of course, but there are a couple of other things also. So we don't have a manual describing just C++20 as it is specified now. That's sometimes a little bit tricky, but we have CPV reference. That's good. So there's an interesting consequence of that. The consequence is that what happens if you make that view const? So we might not do that for a good reason, because we may no longer be able to iterate. It depends whether the view cache or not. But if we make the view const, different things happen. So if you have a view that has a ref view, we do not propagate const. So if the view is const, the elements are still not const. This is not the case if we have an owning view. If we have an owning view, then I should explain that here. So unfortunately, in a filter, you cannot see that easily because you cannot use that. But if I would use a drop view, you could see that easily. You could just modify the elements of a const drop view. In a filter view, you can't that easily because we are not allowed to call begin for this view. So, but you can see it in the kind of a trick. You can ask, can you give me the underlying container? And can I modify that value there? Yes, you're allowed to do that. That is supported. If you have an owning view, const is propagated. So that means the elements are const when the filter view that refers to that view is const. So that means depending on how we create the view, whether in the creation we use an L value or an R value, we propagate const or we don't propagate const. Consistency would now be the word to say something here. Yeah, and by the way, the common pattern we had so far in C++ is that we do not propagate constness in containers and collections and ranges. This is completely new, and it happens sometimes. I'm not happy with that. Okay, but you know that. I told you so. So be a little bit careful with constness. Good. Summary. So we have seen that we have interesting behavior regarding caching in a filter view. And we saw some of them mean that especially for hashing the second begin, which means also the second front or empty call, are optimized. If you have a reverse view, the effect is delegated to end. So that's the first thing we learned. So a filter view has interesting performance complexity guarantees. Then in general, a filter view is part of the game of the views, and views in general break several well-established patterns of programming in C++. So you can iterate if the range is const, broken by a filter view. Any read iteration does not change state, broken. Concurrent read iterations are safe, broken. Const collections have const elements, broken. Well, not always, sometimes, which is not better. And there are a couple of examples I didn't have here, or I could not show because in filter it does not apply. There are other views where these things apply. For example, cbegin might have a problem. You have seen that copying state might, a copy of a view might have a different state because the cache is removed. And there's another problem with the zip view, which I don't explain now. We have standardized completely bullshit. But anyway, sorry. Oh, this is recorded, huh? Oh. Beep. Good. So to make this constructive, to say what does it mean for you, besides saying, I don't use views. I know a couple of projects that say the way the filter view and other views are designed is a showstopper for me to allow this to give to ordinary programmers. Too many problems can exist, both compile time errors and even worse, runtime errors. But if you say, no, I know what I do, that's, by the way, what the rangeless people tell me. If I complain, they say, just teach it, Nico. They only have to know what they do if it's not self-explanatory. Good. So please, in the whole world, please tell everybody they should buy my book. 4 million programmers, I will be a rich man. Good. So here are the recommendations we have. Put filters early in the pipeline. Create and use filter views ad hoc. Do not modify elements during the lifetime of a filter. Well, or if you modify, do not break the predicate. Or only iterate once from begin to end. So use it like an input iterator. The rest is kind of a hack. because formally that's undefined behavior, but it works. It might be worth to do caching yourself. So because the existing caching might not be the best. Do not use filters in concurrent code. Never, never. Well, okay, at least do not concurrently call begin, empty, front, or if for them. That means do not concurrently iterate over them and call somewhere else empty. Don't do that. I'm sure we will see problems with that. I'm sure in practice, they might not have an effect unless they have. Because it's very unlikely that you really call begin at the same time. But if you do, you have an interesting effect. You will never find this bug, and you will never understand what went wrong, and you will never be able to debug it. I was not able to create this situation so far for me.
Should there be a not in that item?
Where? Oh, yes. Of course there should be a not. That was just to find out whether you are still awake enough at the end of this talk. So it was a test. You won the prize. Awesome, of course. And by the way, there is a not. Oh, there's not. Why not? I don't understand PowerPoint, but there will be. Okay, there should be one. No. Good. Last advice. Should be updated. Anyway, don't modify element. Don't modify elements via const view. So if you can do that directly, indirectly, be prepared that if somebody that gives you the view switches from an L value initialization to an R value initialization, sometimes suddenly your code is broken. That's it. I hope you learned a few things. Thank you very much for the moment. And let's see whether we have some questions. Time for a few questions.